appropriate behaviors to always wear a mask or face cover, especially when in public places, to maintain a minimum distance of 6 feet from others, to wash my hands frequently and thoroughly with the soap and water. Together, we win this fight against COVID 19. So, for the 5 minutes, I will keep the same screen. You can go through the page. I have shared the link on the group also, so you can download. And those who are present for this lecture, please type your name in the blank space and send me the report. Okay. So done. So shall we start with our regular lecture? So okay, when the screen is visible. So let us start with the today's class for the so the presentation slide is visible in the presentation mode. Yes, it is visible. So let us start with the today's class. So in the last lecture, we have seen some operations on the index, that is index update, how we can perform insertion and deletion whenever we are inserting or deleting a record from the database. Usually we perform by using insert, delete, update command, and how these updations will also update the index also. So okay, these operations we have seen. So these operations we have seen with the ordered primary or clustered indices, and there are two types of subtypes of the indices are there, dense and sparse. So in the both cases we have seen how the indexes are maintained whenever any operation is done. So now we are moving towards the secondary indices. So secondary indices, it means that whatever the storage order is there, that is not in the sorted order as per the attribute. So okay, for example, we have seen this figure. Yes, no, not this figure. Here, if consider right now I'm having elements stored in the ID on the basis of sorting order of the IDs, and if I'm having index available for the department name, okay, so then I can say that the index is a secondary index. And previously we have seen this example also, that here even though we are having index on the salary attribute, here we are having the elements in sorted order for the salary, and these are the record pointers, whereas the actual storage order of the elements is not seen as the index storage order. Okay, so in such cases we are calling this as the secondary indices, whereas if we are having the same order as that of the storage order, that is in the store on the storage also I'm storing in ascending order of that attribute, and in the index also I'm having on the same attribute, just like here that we are having elements stored in the departmental sorted order, and elements are also stored as per the sorting order of the departments. And whereas if with the same storage order, if I'm having index available on the id attribute, So okay, we can see that the IDs are randomly, but in the index, always the elements are in sorted order. Okay, in the index. I'm saying in the index, so that here a random pointers we will hold, and here it is mandatory that we should have a dense index only. Okay, so secondary indices are never sparse indices because element can be anywhere in my storage order, but we are maintaining record for every entry, and that's why the secondary indices are always dense indices. So okay, this we have seen. Add operations also, how to update this. Again, we have seen the multi-level indices where there are multiple levels of the indices are there. Whenever the file size grows too much large, so it is difficult for us to access the sequential complete records. So in this case, we are going towards the uh, secondary indices. So okay, screen is not visible. Here I can see my screen. Okay, I will show. Abhijit, please pin to the presentation that in the people, whatever list is there, within that there are two logins with my name, Sanjuni Kadam and Sanjuni Kadam. And wherever presentation is there, please pin that screen so that the screen will be visible to you. Please check once. Right now, I'm showing the multi-level index diagram. So is this visible, Abhijit? Okay. So let us continue with our discussion. So this was the multi-level index. Then index update, that how we can perform insertion in the dense index, how we can perform insertion into a sparse index. So dense indices, entry is available for every search key value. If it is already available into the index, then we are not performing any changes to the index, but only we are performing changes to the data. So in case of dense, whenever we are going for the insertion, always it will check whether entry is available, and based on that it will insert the element in the database and also perform updations to the index if element is not available. If the search key already existing, then we are having two approaches, either holding up pointers of all the records or only holding the starting record and then inserting the record at the end of the previous record values. So dense indices, this takes much more time for the updations, as because every database entry might result into index updation. Whereas in case of sparse, we are having only limited entries. It means random entry, only a few entries out of complete search key values. And here a maintenance is very low as compared to the dense indices. Same is the case of deletion. If we are deleting the element and that was the only element with that search key value, we are deleting into the database, from the database as well as from the index. If the element which we are deleting is not is not the only element, and this is any, it means not pointed by the index, then we can remove the element from the database, and the index updation not required in case of sparse indices and in the dense also. So here, as compared to the dense, we are having very low cost maintenance for the sparse. Next, we will start with the secondary indices. So secondary indices, it means that the storage order of the search keys is not seen as the index order, and hence we are calling this as a secondary or also non-clustering indices. So here we should keep in mind that these are always a dense indices. There is no concept of sparse secondary indices. Yes, this is a subtype of ordered indices, and this is always a dense indices. That entry for every random or every search key value is available. Okay, so here the procedure, whatever we have followed for the dense deletion and insertion, the same procedure we can apply for the secondary indices. And here it always go through the approach that for every index entry, that is every search key entry, we are having the matching index entry. And hence, even though the search key is having multiple instances, multiple pointers will be there into my secondary index. So this was the secondary indices. So indices on multiple keys. So up till now, it means we are having index on only ID, or we are having index on the department name, or maybe name, etc. On single attribute, we are defining the index. But here index on multiple keys, it means that more than one attributes we are using as a search key attribute. Search key attribute is an attribute on which the index is defined. Okay, so previously we are having index on the ID, we are having index on the department name, but here if we combine these two attributes together, then here such indices are called as a multiple key indices. Okay, so such uh, indices are used whenever we are having always repeated values on the first attribute. Okay, this is the second criteria. It means the second attribute will act as a second criteria whenever we are sorting the elements. So okay, let us read the definition. A search key containing more than one attribute is referred to as a composite search key. That more than one attribute is a part of our index. The structure of the index is same as that of any other index. Yes, whatever previous indexes are there, in the same way these are also there. The only difference being that the search key is not a single attribute, but rather it is a list of attributes. So okay, not only two, not only three, we are having it means more than one, any number of the attributes as part of our search key. The search key can be represented as a tuple of values of, of the form A1 up to AN, where the index attributes are A1, AN. The ordering of search key values is the lexicographical order. Okay, lexicographically it means that increasing order of the elements. If I'm having integer, then integers in ascending order. If we are having alphabets, then alphabetical order. It means in this way, that is from smaller to larger. The same order is followed for the search key values. Clear with this multiple key? Few of the students always join on time at 2 p.m., 3 p.m. Is this a time to start the class? Next, it means how we can decide it. If it is more than one attributes, then how we can decide? So here an example is given. For example, the case of two attributes. It means we are having two attributes A1 and A2 for the storage of search key value. And in the same way, there are two values that A1, A2 and B1, B2. So if you wanted to differentiate between this tuple, that A1, A2 and B1, B2, then we can perform the sorting of this by using check first for the first attribute whether A1 and B1. If A1 is less than B1, or first attributes are same and second attributes A2 is less than B2. If this order is there, then we can say that this is a lexicographic ordering, and it's basically the same as alphabetical ordering of the words. Now here comes the another index files. So let me know. Have you studied this B plus tree in the data structures? Can anyone give me what is mean by a data structure or what is B plus tree? You might have heard about this. Yes. So okay, no one is willing to answer my question. So let me answer the question now. So
Ma'am,
B plus
ma'am,
tree.
ma'am,
Yes. Yes. Yes.
in B plus tree, in B plus tree, the one node having only one key means.
Okay.
Yeah,
Only
that.
one thing. Is it final?
Hello.
Yes. Is it mandatory to have only one key?
I didn't get what you wanna ask, ma'am.
My question is, have you heard about the data structure B plus tree?
Yeah, means that thing. Only one thing I know means the no means there are leaf nodes and node are having only one key.
Only one key.
Yeah.
Okay. So let us see what is mean by a B plus tree. Okay. Uh, so here, the main disadvantage, which means here we have seen multi-level indices. We have seen it means secondary ordered or primary or clustering indices. The drawback of these index files is that whenever my record length goes on increasing, so the performance of these index files goes on decreasing. Okay, and because of this, using use of index doesn't make any difference, and this gives the search it means data access time same as that of the without using the index. Okay, as there are lakhs and thousands of records might be there, and for this purpose for retrieving the data it takes too much time for the retrieval, and the operations are costly because always we perform access of the some part of the data or only limited data we access, and for this purpose we are moving towards the non-linear. Okay, here the main word is that whatever previous index files we have seen ordered, secondary, or it means subtypes that primary and secondary, all these are linear data structures, and now we are moving towards the non-linear index files. Okay, so before that we must study what is a non-linear. Non-linear, it means that this is a graphical structure is there where the access time of every leaf node is same. Okay, so here whatever leaf nodes are there, these are always at the same height or same distance from the root node. That is the main point. Here a retrieval of any record takes the same time as that of accessing any of the randomly record. Let it be 1000 or let it be 2000 or any thousand or first or second record, etc. It takes the same amount of time to access that data. That is the main thing about the B plus 2. So, okay, let us read first initial introduction. The main disadvantage of the index sequential file organization is that the performance degrades as the file grows, both for the index lookups and for sequential scan through the data. Yes, that is true that whenever our file size grows or record length grows, we are having the same problem. The B plus tree index structure is most widely used of several index structures that maintain their efficiency despite insertion and deletion of data. Okay, so it means that here these are maintaining its efficiency. It means the performance remains same even though we perform many insertion or many deletions. Okay, A B plus tree index takes form of balanced tree in which every path from the root of the tree to the leaf of tree is of same length. Okay, as I mentioned, to access or retrieval of any data member access, it takes the same time. Whereas in case of sequential, it depends when I can find that record, how much time it takes. Okay, so here we are having the same access time for retrieval of any record, and each non-leaf node in the tree has between n by 2 and n children, where n is the fixed for a particular tree. So okay, here comes the order. Okay, so let me show you the figure first. Okay, not figure, let us see first thing only. So B plus tree indexes are alternative to index sequential files. So disadvantage of index sequential file: performance degrades as file grows. Since many overflow buckets get created, periodic reorganization of entire file is required. Okay, so that is true that whenever our file size grows, we insert buckets. It means extra space, and reorganization of those records again it takes a time. And advantage of B plus tree index files: automatically reorganizes itself with small local changes in face of insertion and deletions, and reorganization of entire file is not required to maintain the performance. Okay, as in case of sequential file, we always need to update the index, and wherever much more deletions are there, there we need to free the pages or many more overheads are there. But whenever it comes to the B plus tree files, it takes very less space even though we perform many of the insertion and deletion. Still, it takes very less time for the reorganization or keeping the data minimum. Disadvantages of B plus trees: extra insertion and deletion overhead and space overhead. Yes, this takes a lot much space as compared to the index sequential files. And here, insertion and deletion might result into multiple operations. It means previously, in case of sequential files, we are updating the index as well as the database. But in case of B plus tree, we might need to perform updations as more than two places. Okay, actual database operations, and in the index also at more than one place also we may need to perform the changes. There is a disadvantage, and as compared to the advantages are much more in case of B plus tree. Okay, so this is regarding the start. So let us see how this actual structure is there. So this is a properties of B plus tree. All paths from root to leaf are of same length. Yes, these are all. It means from root to leaf takes the same length. Each node that is not a root or leaf has between n minus 1 and n children. Okay, now here we are at the main point. So, okay, in case of sequential structure, we are not deciding any order, etc. But in case of B plus tree, okay, in case of B plus tree, we it means for every tree there is a fixed order is there, and on basis of that order it decides how many elements it can store in that node. Okay, so here we are having different nodes. Node each element, or it means just like memory assignment. It means whenever we are inserting any record, it decides to insert a record on the basis if space is free, it will allocate the space. But complete node will be added whenever any new insertion is there. Okay, so here Okay, let me show you the node structure. Yeah, this is a node structure. B plus tree node structure is there. So if I'm saying that order of the given tree is n, so there will be n pointers will be there. Okay, n pointers will be there and n minus 1 keys will be there. For example, if I'm having order 4, then there will be 4 pointers will be there and there will be 3 search key values will be there. 4 pointers and 3 search key values. Okay, this is the exactly structure of a node of a B plus tree. And in the same pattern, we are having all the nodes of a tree. And hence, whenever it comes to the grow or a deletion, or it means insertion of a node or a deletion of a node, each node structure will be in the same format. That pointer key in the same format it will be there and with the same fixed structure. N pointers and n minus 1 key values. So okay, so whenever we are saying that order n is there, it means that this refers to how many pointers it stores. Okay, so each node can have n minus 1 search key values. If I'm having the order of the node is 4, then there are 3 search key values are there. If I'm saying the order of tree is 5, then there will be 4 search key values will be there. N minus 1, 5 minus 1, 4 search key values will be there. Then why this complicated structure is there in case of trees? Okay, let us see. So each node that is not a root or leaf has between n minus 1 and n children. So root it means that very parent node is there and from that the tree grows in downward direction, left right and left right. Two subtrees will be there and whatever the last end node will be there where actual records are there. At this point, those will be called as a leaf node. So the leaf node is the last stage where further the tree doesn't go. Okay. So root or leaf node each will be having more than or equivalent to the half number of the children. Okay. A leaf node has between n minus 1, no, n minus 1 divided by 2 and n minus 1 values. Yes. And special cases, if root is not a leaf, it has at least 2 children. If root is a leaf, okay, that is there are no other nodes in the tree, it can have between 0 to n minus 1 values. So okay, these are the things which at the start seems very difficult, but as we carry on with the explanation, this will become very much easier to understand. So let us go by one by one. And when it comes to the insertion or after completion of the insertion of B plus tree, you will be clear with the complete idea of the B plus tree. Okay, at this point, this seems very difficult, but it's not. This seems like a bombarding each and everything, but actually these are the properties of a tree. Okay, so let us see the structure and then let us see few of the operations and then we can go for the insertion. Okay, so now here a structure of a B plus tree. How it means how the nodes of B plus tree are there. So these we are looking. A B plus tree index is a multi-level index, but it has a structure that defines from that of the multi-level index sequential file. So okay, this means that this is same as the what we studied regarding the multi-level indices, but it is having a horizontal structure as compared to the multi-level indices. Okay, it contains up to n minus 1 search key values, that is k1, k2 up to kn minus 1, and en pointers will be there p1, p2 up to pn, and the search key values within a node are kept in a sorted order. Yes, if it is an index, it means it will be always sorted. If I is less than j, then K of I should be always less than K of J. That is the main rule. Okay. So here this is a some structure of a B plus tree index. So here right now we are having n equal to 4. So I hope you can see the figure clearly. So here we are having the order of the tree as 4. 4 it means that there will be 4 pointers will be there, and there will be 3 search key values will be there. Okay, this is the main thing. N equal to 4, it means n minus 1 will be equal to 3, and hence there will be 3 elements or key search key values will be there, and there will be 4 pointers. So let us only concentrate on this. This is a leaf node. Leaf node, it means very last node in the tree through which records are connected. So let us see the structure. So right now I'm having 3 values: brand, Califrame, and cream. So these are the 3 values. So you can see that these 3 are in a sorted order. So in order to point those records which are less than brand are there, so this pointer will be used. So this pointer will be always pointing to the records which are less than brand. But right now, as this is a leaf node, this will be actually pointing to the records. Okay, the actual records in the database. So this will be pointing to the brand. This will be pointing to the Califree, and this will be pointing to the creep. Okay, so this is the actual structure of a leaf node is there. So please have a look at this for a minute. May I move to the next slide now? Please, if in between you are facing that the concept is getting too much difficult and you are unable to understand, we can skip the current explanation and we'll move to the some examples. Yes, I'm going to cover the examples, but right now I feel that you are getting whatever I'm trying to say. If not, then let me know. I will go for some examples and then you will understand the complete structure.
Ma'am,
Yes.
if you want to access the record of Kim, then means how it will happen? Like, uh, what we can say, Crick is containing record lesser than it means. So Kim is greater than it now. So how it will access? Or
Actually, yes, yes.
mm,
Complete your question.
then means there is only three leaf node are there, and means how it will access the question is came my mind.
Okay, so here, main thing is that here you might have seen this pointer to the next leaf node is this. Okay, pointer to the next leaf node, it means that after creek, okay, right now there are 11 to 12 records are there. After creek also there might be remaining records will be listed here. Okay, if I take these names, so these names will be arranged in alphabetical order, and based on that, these three are the first entries. And after create, consider that there is a Gold is there and Ilsed is there or Einstein is there. Okay, these three records will be there. Then here will be exactly the same structure will be there as compared to this leaf node. Okay, म्हणजे हे आता जसं हे लीफ नोड आहे असंच लीफ नोडचं स्ट्रक्चर याच्या पुढेही इथं अटॅच केलेलं असेल. त्याच्यामध्ये या तीन व्हॅल्यूजच्या पुढच्या व्हॅल्यूज येतील सॉर्टेड ऑर्डर मध्ये. ओके, आणि कन्सिडर दॅट त्या तीन व्हॅल्यूज आहेत गोल्ड, आईन्स्टाईन आणि इल्से. ओके, E, F, G, it means that I, Einstein, Ilsted, and Gold. In three ways, these records will be there. So right now, order is 4. It means that we cannot store more than 3 keys. So whatever the remaining keys are there, that need to be stored into another leaf node. Leaf node. Then here one more leaf node will be there. The first in that entry will point to the Einstein. Next will be Ilse, so that will be pointing to the Ilse pointer. And next whatever gold is there, similarly gold will be also pointing to the given record. Again, whatever the fourth pointer will be there, so here will I will have in Einstein, Ilse, and gold will be there. So in this way, these pointers will be there, and again it will again hold the pointer to the next leaf node. So after these three records, consider I'm having Mozart, Singh, and Kim. Sorry, I'm having Yeliaminke. So it means that I will have first Mozart, then I will have cuts and keep. These three entries are there. Then there will be exactly a same leaf node will be there, which will be pointing to these records. So if consider that I wanted to search any of the kin, it means any search key, then from the root node only I will. So this is only the 1/5 part of the complete structure. So let me know whether I have placed any of the records. Okay, this is not the exactly. Okay, let me check from the book whether I can give any figure, etc. Yes, I'm having the figure available with me. So now, can you see the complete figure? So here, previously I said these are the first three records will be there, and this will be a complete B plus tree structure for a given database. So here labels are given. This is my root node, the very first record from where insertion or deletion operation or search operation starts. So here, these intermediate records, these will be intermediate records, or which are also called as non-leaf nodes. This is a root node. This is a internal nodes or non-leaf nodes, and the it means entries or leaf nodes which are actually pointing to the records are there. So these will be called as a leaf node. So always the tree grows in upward direction. It doesn't come in downward direction. It grows in upward direction. So insertion will be at this point. So whenever this node will be full, then this will split and will send the middle pointer to the upward direction, and hence it will check for the empty space. If available, it inserts, else it again sends to the previous state. Okay, so this is the database record as compared to the B plus tree index files. So you can see whenever I wanted to access any record, so consider we wanted to search the key value. So okay, if key value we wanted to search, so always we should start searching from the root node. Okay, at the root node, this will compare key value with the Mozart. So now Mozart is a value which is greater than the key. LMK. It means after LM after K M comes. Okay, so that means that there is a possibility. So this is a left subtree and this is a right subtree. So you can see there are two pointers uh, on the left side and right side of the Mozart are there. So whatever the left node is there, so this left pointer always points the record which are having value less than the Mozart. Okay, and whatever this right pointer is there, this always points to records which are having value greater than the Mozart. Okay, and the same rule follows to the every record or every key in the this tree. Okay, so if we consider the Einstein, okay, Einstein, if I wanted to search for the creek, so I will search at this point. So creek is smaller, so I will go to the left subtree. So again I will start from the first point, that Einstein value is greater than the creek, so I will look into the left subtree. So at this point I will compare the creek value with this, not found, not found, and not found. So here the comparisons I need to perform in order to search the particular value is at this point 1, at this point 2, at this point 3. If consider that the value is in between here, it means very less comparisons. I always should go for accessing the tree. So this is called as a height of the tree. Height of the tree, it means that how long is my leaf node from the root node. So this will be always at the level 0. This will be always at the level 1, and this will be level 2. So all the nodes will be at level 2 only. So for a minute, please check this diagram. So okay, clear with the structure of B plus tree in the database. Actually, I shifted to the presentation mode. Why this presentation mode is not visible? Yes, it's visible. Okay, so here you can see that this is a root node. So whenever we are trying to insert or delete any record, so always the lookup or searching where to insert my record always starts from the root node. So whenever we are trying to insert any record, always the comparison starts from the first point, that is Mozart or root node. So in the root node, this will search whether element is found at this first key element only. If found, it means that always, it means again there are two types are there in the B plus tree, left oriented and right oriented. Left oriented, it means that whatever this search key value is there, for that record is available into a search key only. And right oriented, it means that whatever the search key we are searching, that can be found in the right subtree. Okay, it means just like Mozart is there, Mozart I can find in the right subtree. Similarly, Srinivasan, this will be again available at this point. Einstein in the right subtree, Gold also into the right subtree. Okay, this is how the nodes are getting repeated. And left subtree, it means that whatever leftmost point is there, this will be at available at this point. Okay, creek will be found at this position. So okay, either this value will be repeated at this point or at this point. So any point we can refer. If this is getting repeated in the right subtree, this tree will be called as a right oriented, and this, if Einstein is getting repeated at this point, this will be called as a left oriented trees. So okay, this is the structure of a B plus tree. So please, if you are having the doubts regarding the structure, then it will be useless to go for the further operations, etc., or learning the properties. So here main property is that if we are having the order as a 4, okay, if we are having the order of the elements as 4, then here there will be n minus 2. It means 4 divided by 2, 2 to 4 records will be there. Now let us come to the calculation. Okay, so here, am I audible clearly? Am I audible clearly? So here, definition of a structure of a B plus tree is that. Let us see the properties. All paths from the root to leaf are of same length. Yes, we are having the length as 2 only for the given example. Each node, that is not a root or leaf, okay, it means internal nodes, has between n minus 1 and n children. Okay, so here if we are having the order 4, okay, n minus 1, that will be 2, and n, it means that there will be 4. So every tree, every subtree will be having 2 to 4 subtrees. Sorry, each node, that is not a root or leaf, has between n minus 1 and n children. So okay, n minus 1, if we are having the order 4, so n minus 2 will be 2, and n, it means 4, so 2 to 4 children will be there. So as you can see, if this neither root neither leaf, okay, so this will be the internal nodes. For this, either we are having 2 to at least 2 and max 4 children will be there. So whatever these pointers are there, these will be called as a childs of this node will be there. Okay, just like for the root, I'm having two childs. For this sub-tree, I'm having three childs, 1, 2, and 3. And for this node, I'm having two childs. Okay, so this is a minimum condition that it should have n minus 1 to n children. Clear with this condition? Each node that is not a root or leaf has between n minus 1 and n children. That between 2 to 4 children will be there if we are having order n. Now, a leaf node has between, okay, how many nodes will be there? A leaf node has between n minus 1, that is 3 by 2, and 3, sorry, 4 minus 1 values. Okay, values, it means that the search key values it is referring. So here, if we are having order as 4, uh, 4 minus 1, 3, 3 divided by 2, we will have 1.5. So here, whatever this function is there, okay, this is always in the, it means upper bound or lower bound will be there. So let us see what is it. 1.5, it means it can be 1 also, and n minus 1, 3 values it can have. It means a leaf node can have 1 to 3 values. So let us see the structure. So this is the structure. So it is a whatever this 1.5 is there, for this upper bound values are taken. Upper bound, it means that a 2 two values it should have minimum. So here we can see there are three values, there are two values, there are three values, 2 and 3 will be there. So there will not be any leaf node with only one value. That is not a possible condition. Always this should have n minus 1 divided by 2 uppercase function and n minus 1 values in that leaf node. So you might have understood this point also. So special cases, if the root is not a leaf node, okay, it has at least two children. Okay, if the root has not a leaf, it means there are some sub trees are also there. It has at least two children. So for the Mozart, Mozart is right now not a leaf. If it is a leaf, then this can directly point to a single record. But if this is not a leaf node, that only one record is there, Brand or Caliph or Creek, etc., then this may be very first node or this is maybe very last node. But right now, as we are having this not as a leaf node, so this may condition is that it should have minimum two children. Yes, that condition also satisfies. Next, if the root is not a leaf, sorry, if the root is a leaf, that is, there are no other nodes in the tree, it can have between 0 to n minus 1 value. So if it is the initial insertions are there or only 3 to 4 records are there, then we can have only 0 to n minus 1 records. So 0, no elements, 1, 2 and 3 records. 0, no records, or we can have 1, 2 and 3 records here. So whenever root is a leaf only. So now I hope you are in position to understand this explanation. So take a minute, read these rules and we will come back to the explanation.
Ma'am,
Yes,
can you open that page where the structure is there?
okay, I will open. Visible?
Yeah, this one. Means from what basis we decide the uh, that 15151 value is the root?
Actually, this will be clear whenever we are starting with the operations. Okay, so when we perform insertions, so actually at the start only a single node will be there. Okay, म्हणजे
No,
फक्त एकच नोड असणार म्हणजे ऑर्डर कशी डिसाईड करणार असं म्हणताय का तुम्ही?
नाही मॅम, मी काय म्हणते, ते कशावरनं डिसाईड केलं की हेच रूट घ्यायचं? मीन्स आता तर इथं हे आयडी जे आहेत ना, मग
हा
ते
हा
तर
हा.
ह्याच्यावरनं नाही, मग तेच का घेतलं रूट नोट, दुसरं का घेतलं नाही असं विचारते.
नो 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 ऍक्च्युली म्हणजे तुमचं इन्सर्शन रॅन्डमली कसंही असू शकतं. पण
ओके.
तुमचं स्ट्रक्चर मात्र याच फॉर्मॅटमध्ये येतं. ज्यावेळेस आपण ऑपरेशन्स चालू करू ना त्यावेळेस आपण तुम्ही ऑर्डर सांगाल त्याच्यानुसार आपण ट्री डिझाईन करूया. ओके.
ओके. ओके.
ऍक्च्युली दिस इज म्हणजे कुठल्या वेने तुमचं इन्सर्शन होतं त्या टाईपमध्ये ट्री माझा ग्रो अपवर्ड डायरेक्शन मध्ये होतो.
मीन्स फर्स्ट कोणती व्हॅल्यू ऍट द स्टार्टला इन्सर्ट केली तसं म्हणताय का?
हा तसं काही नाही इंडिपेंडेंट आहे ते.
ओके.
हा
नोट.
तुमचा ट्री सेमच येणार. तुम्ही कसंही इन्सर्शन करा तुमचा ट्री हा सेमच येणार. Anybody else is having doubt regarding the structure? If not, then we can shift to the operations on the B plus tree. So here, whatever search key values are there, these will be always having in the ascending order. That K2 will be K1 will be less than K2, K2 will be less than K3, or similarly I and J will be there. And whatever the sub nodes or sub trees or childs are there, so these will be having values less than k1 only. Okay, so right now we are having the right oriented left sorry b plus tree. So whatever the children or child pointed by this p1 will be there, so this will have values less than k1 only. Whatever the pointers given by the P2 are there, this will be between K1 and K2 will be there. Okay. So this is the structure of always a B plus tree. So this is a leaf node. So this is the complete tree. So properties of a leaf node, the same properties that less than greater than are there. So for I equal to 1 to n minus 1. Okay. Properties of a leaf node. Pointer pi either points to a file record with search key value ki or to a bucket of pointers to a file record. Each record having search key value ki. Only need bucket structure if search key does not form a primary key. Okay, if LIDLJ. Okay, let us see the first point. So first point says that we are having 1 to n minus 1 pointer. Sorry, yes, pointer. Uh, for I equal to 1 to n minus 1, pointer pi either points to a file record with search key value pi. Okay, right now let us consider this record only. Okay, so right now order equal to n equal to 4 is there. So 1, 2, 3, 4 or 1, 2, 3 right now n minus 1. So 1, 2, sorry, and 3 will be there. So this is a 3, and whatever this structure is there or this pointer is there, this will be pointing to a, so this pointer, that p1 pointer less than the ki will be pointing to the actual record or this might be pointing to a left subtree. Now we will take an example of the Einstein example. Einstein example follows this both rules. Okay, now this is my non-leaf node. So there are pointers P1, value K1. This is pointer P2. This is value K2, and this is pointer 3 will be there. So mean max condition satisfied during the rules only. We have seen that we should have at least these many search keys. Sorry, leaf nodes. These non-leaf nodes, they can have 2 to 4 childs. So now the condition satisfied. So now we are talking about this subtree. Next, left to the Einstein. Here, this says that the pointer pi either points to a file record with search key value kr. Okay, so here, if I'm talking about the Einstein, this is my K1 and this is my K2. This will be my P1, this will be my P2, and this will be my P3. So either this is pointing to the actual record. Right now, this is not an actual record, search key ki, or to a bucket of pointers to the file record. Actually, we are studying about the leaf node. That's why. So we must consider only this node only, Einstein. So this is my K1, this is my K2, and this will be pointing to the actual record. Yes, actual record is there, Einstein, or this is pointing to a bucket of pointers to the file records. Okay, right now I'm having B plus tree on the name of instructors. So here neither of the name is getting repeated and name is neither my primary key. So it means that repetition can be there. If repetition is there, that value, that Einstein will not be repeated into the index. In the index, this will point to only single value. So if I'm having the Einstein here, then instead of having a single record, we will use a bucket. Bucket, it means a storage of memory record. Okay, where multiple records I can store, and this will be pointing to that multiple records or block of memory. So okay, let us read the explanation. So for I equal to 1 to n minus 1, pointer pi either points to a file record with search key value ki, that it is pointing to an Einstein record, or to a bucket of pointers. Bucket of pointers, multiple records are there to the file records, each record having search key value ki. Yes, every value will be having value Einstein only need bucket structure. So here, when to use buckets, that is required whenever that search key value is not a primary key. Okay, that search key should not form a primary key. If that is primary key, then there will be a single record and there is no need of bucket. And how this bucket should be used, how that bucket structure should be maintained, that is decided as per the structure. Okay, this is the first point regarding the leaf nodes. Now next, if Li, Lj are leaf nodes, okay, Li, Lj are leaf nodes and I is less than j, then Li's search key values are less than Lj's search key values. Yes, let us take this records. So okay, If Li and Lj are leaf nodes and I is less than j, then Li search key values are less than Lj search key value. Okay, so let us take an example here. If this is leaf node and this is leaf node, this is k2, this is k1, then it is always mandatory that this value is greater than this value, or this value is smaller than this value. So you can see these all values are in increasing order. Okay, so this whatever the leaf structure is there, it always sorts the elements and every element is available at the leaf node also. Pn points to next leaf node in the search key order. So this always explained here. So this in the book itself, this mistake is there that whatever this pointer is there, that should not be at this position. This should be at this position in between the creek and Califree. So here, this whatever the Pn, this is my P1, this is P2, and this is P3. Order equal to 4 and 4 n equal to 4. So this will be always pointing to the next leaf node. So you can see the chaining is there. And hence, whenever we are searching for a record or sequential search or look up onto the complete file system is there, we can start from this and can access the next element sequentially. Okay, go through the rules. Clear? Now, some properties of the non-leaf nodes form a multi-level sparse index on leaf nodes. For a leaf node with m pointers, yes, all the search keys in the subtree to which p1 points are less than k1. For n, for 2 less than I less than n minus 1, all the search keys in the subtree to which pi points have values greater than or equal to ki minus 1 and less than ki. All the search keys in the subtree to which pm points are greater than the k of m minus 1. So this is regarding the non-leaf nodes. So sparse indexing means that we know these are having not every entry but limited entries are there. Just like here, these many entries are there. Einstein is there. So in the sparse index, whenever we are trying to search an element, if this is pointing to this record, our record may be in the this subtree. So in this way, we can start searching. That's why this is called as a multi-level sparse index. For this complete sequential records or sorted records, we are deciding a sparse index. This is regarding the value less than and greater than. This is also one of the examples. Now here the order is 3. Order is 3, it means that 3 pointers and 2 search key values will be there. So this is the example for the right oriented subtree. Right oriented, every this record will be available into right sub child or right sub tree. Now poor is on the B plus tree. Now here your any doubts are there or any detailed explanation regarding how the operations are carried out, that will be taken. So now here for this, let me shift from presentation mode to the any normal mode. So instead of taking alphabetical values, let us have explanation on some integer values. So okay, I'll take a table for this. How much order I should take? Four should I take? So okay. So this will be P1. This will be P1. This will be K1. This will be P2. This will be K2. This will be P3. And let us take off order 4. So this will be K3 and this will be P4. Okay, these 4 pointers we will take, and this row we will delete. So now, if consider right now I wanted to insert random values. Let us take 25 is there, then 10 is there, then 23 is there, and then consider 50. And let us take 10 values or 7 values at most we will take. 7 I will take, then 60 I will take, then 50. 7 values are done. Yes. So now in this random order, my elements are getting stored. So initially, whenever we are trying to perform any operations, always my tree will be empty. Empty tree, the same structure, whatever I am having right now, this structure will be there. So the same empty structure will be there. So okay, these empty structure right now. So elements insertion will be done at this key values. Okay, K stands for the key and P stands for the pointer. So insertion will be done at these values. So right now this is my root node of a B plus tree. Now 25 I'm trying to insert as this is the only node or this is the first node. So I will enter at this position. 25 will be inserted. Now next is the 10. So 10 is a smaller element as compared to the 25. So then 25 will be shifted from first position to the second position, and 10 will be inserted here, indicating that right now this is a sorting of the order. Now 23 is there. For inserting 23, this will look up starting from the first point, 10, again 25. 25 is greater, so this will shift 25 from this position to the next position. So now 25 got inserted. Right now, what are pointers are there? I will change the font of the black I will take. Okay. So whatever white values are there, these are my actual records or these are my nodes, and these are my pointers. So pointers, this will be pointing to a record of 10, this will be pointing to a record of 23, and this will be pointing to a record of 25, and this will be right now empty as there is next no node is there. Now consider these three values we have inserted. Now I wanted to insert 50. Okay, whenever this right now whatever node is there, right now my node is full, there is no space available for insertion of my node. So as per the sorting order, okay, sorting of the order, right now we have inserted 10. Sorting order I will take 23 and 25 are there. Whenever the 15 comes, I should have the order like this. Okay, this should be the appropriate order for the searching. but as my node is full, I cannot insert 15 in between. So here, whatever this actual pointers are there, these will not be changed. But whatever node is there, this will result into a insertion of a node. Another node will be inserted. Okay, another node. So 10 and 15. So whenever node will be split it means that two elements will be in one tree and these two will be in another subtree. Okay, this will be in one subtree and this will be in another subtree. So here a left orientation and right orientation, it means that after the splitting, okay, so whatever after the splitting of these elements, whatever the this left, sorry, right part is there, that will be sent as a root node. Okay, so whatever this 23 is there available on the right hand side as the first element, that will be inserted, that will be sent above as a root node, and hence we will have a new structure of our nodes as this one. And here this will have 23, this will have 25, this will be empty pointing to null, and my record structure will be something like this. P1, here 23 as it is will be there, because here right now this will be pointing to a left subtree, and we will have a pointers like from this point to this point, one point. That P1 will point to the tree subtree with records less than the 23, and we will have a pointer P2 pointing to these records of this subtree, which is having records less than greater than or equal to the search key values. So this is P1 and this is K1. So all the elements which are available in the P1 pointer are there will be always less than K1, and whatever the records available in P2 or pointed by the tree in by the P2 are there, this will be either equivalent to the 23 or greater than 23 will be there. I hope you are getting with the explanation. Still we are going to carry out insertion operation, but if you didn't understand the split up of this, let me know either in the chat window or some other medium. Yeah.
Ma'am, explain once again.
Okay. So here, fact is that we wanted to insert these records. Okay, initially 25 is there, so my tree will be empty. So what your key K2 values are there or K values are there, their actual key records or key values are stored. Right now, this is I'm dealing with the search key as an integer value. So initially my 25 value will be there. So 25 will be inserted at the first key value, okay, at the first position. Now next, I wanted to insert the 10. Okay, 10 value is less than the 25. Okay, so it means that I should have the order like 10 first and then 25 should be there. So whatever 25 is there, that will be shifted. Sorry. So that will be shifted to the next key value, and whatever the first position is there, that will be assigned with the 10 value. Okay, so these are the P1 record, that is pointers to the actual record. So P1 will be pointing to the actual record 10 into the database, and P2 will be actually pointing record of 25 into the database. Now next I wanted to insert 23. So 23 also. So 23 also comes before the 25. Okay, so 23 will come here. It means that whatever these two positions are there, again need to move to forward, and hence at this position I will have 25, and at this position I will have 23. Now the sorting order 10, 23 and 25 will be there. So now again after that I wanted to insert 15. So 15 alphabetic, that is lexicographical order, increasing order. It comes at this position. Okay, not at this position, but it comes to this position 10, 15, 23 and 25. But as I am having order n equal to 4 only, it means that k values will be, it means key values will be 4 minus 1. 4 minus 1, it means it can hold only 3 key values. But there are 4 key values are there. So in order to tackle with this problem, it will be split up. Split up, it means that whatever this complete structure will be there, that structure will be divided into two parts. A left part, that is from the middle only. Left part will be having values less than the middle value, and next part will be having remaining values. So here, whenever we the split up carries out, so this two trays uh, will not be uh, it means two trays will not be kept hanging into the memory. So in order to connect these two as a one part, we always connect them by using the root node. Okay, previously only one was there, that's why that was acting as a root node. But now as one node cannot hold all the elements, so this node will split up and will send the middle element to the root node. So this 23 will be acting as a root element. Root element, it means that whatever this right part is there, right part, 10, 15, 23 and 25 is there. So leftmost right part or rightmost left part, either 15 or 23. There are two variations, but right now we are dealing with the right variation. So this 23 will be acting as my root element. So root element, this 10 and 15 will be into one root or one leaf element, one node, and remaining two elements 23 and 25 will be there available into another node, and 23 will come go upward holding the acting as a root node, and these two will be acting as a leaf node. Now are you clear with this?
Yeah, ma'am, it's clear.
Okay, let us go for the remaining insertions. Now up to 15 we have studied. Now 7 I wanted to insert. So 7, so it will start looking from the P1. So it will search for the first search key value. 23 is greater than the 7. So it will come to P1 and will start browsing. So first key value is 10. 10 is greater than the 7. It means that 7 should be inserted here. So it will check whether in the current node space is available. Right now there is one empty space. So this will perform the insertion like 15 will come here, 10 will come here, and 7 will come at this position. Okay, so in this way the insertion will be done. Next is 60. So start browsing from the root. So P1 23 is there. So 23 is uh, smaller than the 60. So it means possibility of storing the 60 value is into the second part. So this will come at this position 23, 25, 60 value. So 60 value will be inserted this position. Now we wanted to insert 50. Okay, for inserting the 50 value, so again it starts searching from this P1. 23 is smaller, so this will go to the next point. So second key value is not available. It means that space might be available for 50 at this position. So 23, 25, 60. So right now, after inserting the 50 value, I will have sequence like, it means desired sequence is like this. Now, as this node is also full, we cannot insert 50 at this position anywhere. So again, this should go for the splitter. So split up, it means that from in between split up will take at this position, and hence 50 will be assigned to the next root value. So hence whatever this complete node will be there, that will be split up. And we will have structure like this. 23 and 25 will be in one node. 60 will not be a part of this, and 50 we are sending to the next value. So 50 will come here, and here also 50, and here it will hold the value like 60. This node will be blank, and there will be a pointer from P3 to this node. So let me compact the structure. So in this way, the structure will be there. And this will be, P1 will be actually pointing to a record of 50, P2 will be pointing to actual record of 60, and P3 holding the blank. Similarly, 23, 25, 17, and 15 will be there. So in this way, the tree grows in upward direction, not in downward direction. Shall we perform few more insertions? Okay, let us go for a few of the insertions. I will take after the 50, I will take 40, I will take 20, and I will take 70. Okay, three insertions we'll study. So, in order to insert these records, so what we will do? Next, I wanted to insert 40. So let us take where we can insert the 40. So it will start from the K1 value. K1 value is greater. So look into then K2 value. P50 is greater than the 40. So it means that there is a possibility of inserting 40 in the P2 child. So in the P2 child, space is available. So 40 will be inserted here. Next, we wanted to insert 20. So 20 should be, first it search for the first search key value. This search key value is greater than the 20. So it means that 20 should be part of the P1, the child pointed by the P1. So right now P1 child is having these many elements: 7, 10, 50, and 20. Okay, these four elements are there. So if you wanted to perform as right now the child node is free, child node is completely full. So it means that we should go for the split up. So So splitting of these elements at the middle will take place just like this. So it means 15 leftmost right. Sorry, yes, leftmost right. First element we are sending to the next node. It means 15 should be sent above. So this will act like, so instead of P1, P2, P3, I will use only 1, 2, 3. As splitting is done, it means that whatever this node is there, so there will be two subparts. 15 and 20 will come here, so this will be blank. And one more node, 15 will come upwards. So here you might think that there is no space here. No, it's not like that. Actually, this node, that K3 value is free. So instead of having K3 value at this point, so this will be shifted here. 50, 23 will be shifted here, and at this position 15 will point. Okay, and hence pointers will shuffle like this. P4 will be pointing to this, P3 will be pointing to this. Now, in this way, the tree will shuffle like this. So any new insertion still you are willing to perform? 70 is remaining. For inserting 17, this will perform lookup into the root node. 15 smaller, 23 smaller, 50 smaller. It means that 70 must be filled in the P4 child. So P4, 50, 7, 60 and 70 space is available. So 70 will be inserted this position. Right. Any new insertion you are willing to perform? So please let me have doubts. If you are having doubts, please. So you, by your own, try to insert in the same tree 80 one value, 27, and try to insert 70. These three values I expect you to enter in this. So this previous values I will remove. So within the existing tree, try to insert these two values and let me know the answer. Any answer? Okay, I'll continue with the insertion of 27. So for inserting 27, we will perform the lookup 50, 23. 23 is also smaller. 50 is greater than the 27. So it means that insertion of 27 should be in the child pointed by the P3. So it will come to the P3 child. So 23, 27 and 40. So it means that 27 should be inserted at a position like this. Okay, this should be the actual sequence which we must follow in order to split the node. So splitting of the node should be from the middle of the order. So and hence we will have 27 need to be sent as an internal node. Okay, now if we are sending the 27 as a next part, then it means that whatever the current so forget about this. Right now, let us concentrate on the leaf nodes. So this leaf nodes will have structure like so. Here we will have empty, and here we will have 27 and 40, and this will be empty. Yes. The splitting of nodes into two subparts 23 and 25, 24 and 14. So now the question comes whether 27 is placed having the place in the upper node or the next higher level or the higher level. So at this position we learned that 27 cannot be placed here because already the node is full and hence 27 cannot be inserted. Then we again perform the splitter. Splitter on the basis of the same search key values. We are having three values currently 50, 23 and 50. If 27 we wanted to answer, then 27 should be at this position. Okay, 27 is at this position. Then splitting the elements at the middle. So this will split structure into two subparts, 15, 23 and 27, 24. And hence at this position we will get a 27. Okay, it means that right now whatever this structure is there, that will remain as it is, but whatever the internal node is there, that will split up, and 27 will be acting as a root element. These two will be internal nodes. Uh, so here, repetition of 27 is not required in the internal node. Only 50 is sufficient. So today's lecture got too much heavier. So only this example I will cover. So 27 will be pulled by this. So in this way, the things will go. So in detail, we will study into the next lecture. Today we'll stop here.